This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The third lecture is broken into two parts. Lecture-03B covers sequence simulations using matrix operations. The learning objectives for this lecture are to use matrix operations for analytic calculation of simple signals, to understand matrix representation of steady states and transients, to explain the hard pulse approximation, and to build numerical simulations over time and space. Let's review the simple sequence operations. Remember that sequence blocks correspond to simple matrix operations. RF excitation or nutation is given by multiplication by a rotation matrix. Here the rotation axis is given by angle phi in the mx-my plane or transverse plane. Gradient-induced rotation is given by a rotation around the mz axis, and this can include gradient effects or off-resonance effects or other effects. Relaxation is given by a rotation by an A matrix and the addition of a B vector. Both A and B are functions of the relaxation parameters, although B is only a function of T1, since B corresponds to the recovery term of longitudinal relaxation. We can also simulate multiple spins at different positions very easily with loops, as we will see. So let's start with a very simple example. This is an excitation recovery sequence where we rotate by a flip angle of alpha about the negative y-axis. In this example, which you have probably seen before, we will also neglect the transverse magnetization immediately before a radio frequency pulse. We can write the magnetization preceding the RF pulse as M1 and the magnetization following the pulse as M2. If we do this, we can easily see that M2 is simply a rotation applied to M1, as shown in the top line. Next, we express M1 as a function of M2 using a relaxation formulation here. Notice, though, that we also neglect the residual transverse magnetization by zeroing out the top left and the middle elements of that matrix. We have no precession in this example. If we do this, we can actually then collapse the matrix down to a simple equation where we express M1 in terms of itself by eliminating M2 in this equation, and we form this final expression, which is a familiar expression for the excitation recovery sequence, where we can neglect residual transverse magnetization, and this is the well-known T1 weighted gradient echo signal, which we will see much more later. So in this example, we've started with matrix operations, but we've actually been able to reduce this to a single one-dimensional expression. We will see later that we do more complicated examples where we end up with a matrix solution. And again, this is a common example that was used in EE369B as well, and is commonly seen in fast T1 weighted MRI. So the next question is, what do we do about overlapping RF and gradients? When these happen during the same time, we have rotation about different axes simultaneously. So the first thing to notice is that rotations about Z and relaxation commute. That is, they can be applied in any order. However, RF rotations or nutations do not commute with rotations about another axis. The hard pulse approximation is used in RF pulse design and other applications. And in this approximation, we actually apply small rotations sequentially. So if these rotations can be broken into very small time segments, then they approximately can commute. So what we do is we break up the pulse, as shown here in the top right, into small segments. And for each segment, we'll have a rotation about mz and a rotation about one of the transverse axes due to the RF pulse. And this is the basis for Chenard-Leroux pulse design, as well as variable rate selective excitation. Notice you can take this a step further, and you can calculate the rotation about an arbitrary axis by calculating the net B field, which is due to the applied RF pulse, as well as any gradients. Then you apply the rotation matrix about this in small steps, and you should get to a very similar answer, providing with the hard pulse approximation you've broken things down into small enough steps. Notice also that these rotations are changing over time if you have a time-varying RF pulse. Now you can also take this one step further and apply relaxation during these small steps, and this gives you a full Bloch simulation, which we will see later. Okay, this brings us to our first question for this lecture, and I would remind you to look at the question and pause your video and think about it before looking at the possible answers. So the question is, what are the equivalent rotations about z and x of 45 degrees and about x then z of 45 degrees? So here are the answers. And the correct answer here is D. Notice that the axis of rotation is not in the transverse plane. The answer A is wrong because these cannot be equal because they do not commute. B and C are wrong. If you just try starting with equilibrium magnetization, you can easily see this. The actual rotations and rotation axes are given below. These are calculated relatively easily for the rotation matrix. The rotation axes are calculated using eigenvalue eigenvector decomposition. So this can be done in MATLAB quite easily. Notice that the rotation axes are actually different here, and that's why this is shown. Next, we will start to see the power of the matrix operations when we look at steady states that have three components. This is compared to the example we showed before where the steady state only has a single component. Recall that we can propagate over some sequence using a simple matrix expression where the magnetization over 1 tr is expressed as A times the magnetization of the previous tr plus some vector B. Notice that these can be combinations of rotations and relaxation. In the steady state, the magnetization is no longer changing from one tr to the next, so we can equate these two terms. We can then simply rearrange this equation and show that the steady state is the inverse of the identity matrix minus the A matrix multiplied by the vector B. If there is relaxation, there is always a steady state. This is because the A matrix has eigenvalues that are less than 1, and this corresponds to a stable system. So let's look at an example here. If a sequence consists of a rotation about mx of 30 degrees and relaxation, what is the steady state starting at equilibrium? Here are the possible answers. Okay, and the answer is D or E. The magnetization will just rotate in a circle, spiraling inward to almost zero, but not quite zero. So please keep watching these lectures and we'll explain this in more detail. You'll see lots of examples here. But think about this example where the magnetization is simply rotating, and try to convince yourself that this magnetization will go to a very small number. Here is an animation of what actually happens. So you can see how the magnetization goes to a very, very small value. It turns out the value is not quite 0. Okay, now we've looked at steady states. It's interesting to look at transients. This can get quite complicated, but there is some intuition behind this. And transients refer to how the magnetization approaches a steady state. Remember, the steady state is unique given the A matrix and the B vector. However, the transient depends on the initial state of the magnetization. So let's review this. Again, the propagation over 1tr can be expressed as the multiplication by a 3 by 3 A matrix and addition of a 3 by 1 vector B. Notice in the steady state that this multiplication and addition does not change the value. So we have MSS equals A times MSS plus B. We can use this to combine these two equations and write the transient in this expression here. So if we take the difference between the magnetization and the steady state, we see that this difference decays by a simple multiplication by the A matrix. That is, the B vector actually cancels out of this expression. And on the far right, you can see that we can start with the initial magnetization, M0, not the equilibrium magnetization. So if we take that initial magnetization and subtract off the steady state, that vector length will decay according to the A matrix raised to the power of n plus 1. Now, we can use a very powerful analysis, which is eigenvector decomposition, to actually add some intuition to this case. So remember, the eigenvector decomposition of a matrix A looks like this, where we have a V matrix, which is actually the columns of V are the eigenvectors. We have a diagonal lambda matrix, which consists of the eigenvalues corresponding to these eigenvectors, and we have the inverse of the eigenvector matrix. Now, we can write this transient form the same way as above, but in this case we can actually decompose the A matrix as shown here, so that we have the V vector and the inverse of V remain, but the eigenvalue matrix lambda is raised to the power of n plus 1. Now I've colored these differently because of the fact that the V minus 1 actually transforms the initial condition into a basis which corresponds to the eigenvectors. So it basically tells you how much of each eigenvector is excited to start with. Okay, so what amount of each eigenvector do we have? And this is very useful in showing how the magnetization will behave. So we will see this kind of analysis quite a bit later, but we'll start with an example that will hopefully give you some intuition for this. So in this example, we're actually going to look at free precession. We're going to consider relaxation and precession over some interval tau. So here, remember that the magnetization, what we've done is we've applied the rotation first and then the relaxation following this. And overall, again, the m after this interval is written as m equals a times m plus b. In this case, I'm not going to show the calculation, but if we take the A matrix with a rotation about z and relaxation, it turns out we can do the eigen decomposition of A as shown here. Notice that the lambda matrix, the eigenvalues here, are scaled by E2, E2, and E1 from relaxation. And notice that they actually have a complex exponential for the rotation by some angle theta, which is precession. If we look at the eigenvector matrix, here's the eigenvector matrix. We actually have two orthogonal vectors that are in the mxy plane here. Now you might wonder, why is this so complicated? Remember that the eigenvector the eigenvectors here are not unique. So you could actually rotate these eigenvectors, and this would correspond to rotation of the eigenvalues. So it's not unique, but this is a very convenient form for this. So also what you see from this, based on the eigenvalue matrix here, is we have a rotation and attenuation. The eigenvector matrix has vectors that span the mx-my plane and another vector along mz. Notice that these are completely independent, which makes sense because we know that we're going to have transverse relaxation and longitudinal recovery. Notice also that we have free precession. The steady state here is simply the equilibrium magnetization. Now, as I've said, if we take the inverse of the eigenvector matrix and multiply it by the initial magnetization minus the steady state, this actually extracts the transverse magnetization and the longitudinal magnetization. And this can be seen in more detail here. If we start with an initial condition where the magnetization is along mx, then we multiply this by the inverse of the eigenvector matrix after subtracting the steady state. Remember, this gives us an mx and a minus mz because subtracting the steady state actually gives us minus 1 here. If we do this, we get the components that will multiply the eigenvectors. Okay, so the square root 2 here, if we multiply that by the first two eigenvectors and sum that, that will give us mx. It may not be quite as intuitive. And then what we see here in the third component is that when we multiply by the third eigenvector, which is simply along mz, right now we have minus 1 because that's the difference to the steady state. So that gives us the initial condition here. And now we know that if we raise the eigenvalue matrix to some power, what we're doing is we're applying attenuation and rotation to this representation, and it turns out that that will give us the free precession that we've already seen, which if we animate it looks something like this. So there are many more interesting cases of this, and we'll see many more interesting steady states throughout the course. So this is quite a lot to go through, but we just want to give you an introduction of this at this point. But again, typically what you will see is that there is some rotation component and some non-rotating component. This is because there have to be 3 eigenvalues of this matrix A, and one of them will always be real valued, and that will correspond to a smooth decay, and the other 2 usually will respond to some rotational component. Okay, let's turn to another example. This is a short repetition time inversion recovery signal. So the idea here is that we apply an inversion pulse to the magnetization, we wait some inversion time, and we we excite, and then we wait some small echo time and image, and then we have some TR. But we've also chosen this TR to be sufficiently short that we cannot assume full recovery before the start of the TR. This is not really a case that would be used necessarily very often in practice, but it's a nice example to show the power of the matrix calculations. So here we've selected a TR of 1 second, but an inversion time of half a second. The TE is 50 milliseconds, and then we've chosen a T1 of half a second and a T2 of 100 milliseconds. So you can already see that probably the transverse magnetization will die out by the end. However, the longitudinal magnetization, it should be clear by inverting this that we will certainly not recover to equilibrium here. So to do this example, let's think about the operations that we're going to do and sort of write almost a pseudocode here. So we're going to express the magnetization after the 180 as a rotation times the magnetization at the end of the TR that we call MTR. Then we're going to express the magnetization just prior to the 90-degree pulse, just following the 90-degree pulse as a rotation about the x-axis of 90 degrees, and that's multiplied by some recovery term from some relaxation operation on the magnetization after the 180-degree pulse. Then we will express the magnetization at TE as some relaxation following the 90-degree pulse. And finally, the magnetization at the end of TR will express as some amount of relaxation from the echo time. And notice that the duration of the relaxation has been expressed in this sort of expression E, which represents relaxation. So these are sort of operations or pseudocode. These are 3 intervals here. So now what we're going to do is write this using MATLAB and matrix expressions here. Okay, so first we assume that we've written these E2 and E1 expressions as described previously, given the time duration, the T1 and the T2. So we can simply write initially that the A matrix for this first period is basically the relaxation component times the inversion, or the rotation about x of 180 degrees. The corresponding B vector for this is just the recovery term, basically for the interval shown by the 1 here. Next we do the same thing for interval 2. So we have a rotation of 90 degrees, and then that's followed by relaxation. So again, we have a diagonal A matrix using the E2 and E1 expressions. And we have a vector with a recovery term. And we assume that the E1 for B here corresponds to interval 2. We can do the same thing for the third interval here. Again, we have a diagonal matrix for relaxation, and we have a recovery term. Now, we can combine the A matrices for these 3 intervals, and we can combine the B vectors for these 3 intervals. And then we can simply calculate the steady state here, and we'll see that the steady state here is as shown here, where in the steady state there is a small amount of Z magnetization, and this is the signal that we would get at the echo time TE. I'll make one comment here that I didn't really say, is if we look at the propagation, look at the order that we've applied these in, we've calculated this at the echo time. So you notice that the order that we've combined these matrices, we're starting at the echo time and propagating through a full cycle to the next echo time to calculate the steady state. And of course, if we did this in a different order, we would have the magnetization at a different position within the sequence. Okay, so now we can do this a little bit more compactly, and there's a function abprop.m which allows you to propagate spins through a series of A and B matrices, and this is a bit more of a compact way to simulate these sequences. So the function looks like this. The abprop.m is in the MATLAB folder for the class. So basically this is going to return the A matrix, the B vector, and the steady state that corresponds to these. So what you can give this function is a combination of A matrices and B vectors for each operation, something like this. Now, if the third argument is provided, the steady state is calculated, although this is very fast, so it doesn't really matter. We can also pass the matrix, the A matrix here, as a 3x4 matrix, which means that we've basically assumed we're including the A and the B all in one argument. And we can also neglect the vector, the B vector, and then the argument the B is just assumed to be 0. So this works quite well if you want to use this. So then we can apply something like this shown here, where we call this function with something like an A matrix and a B vector. We can pass it the combined, or we can pass it just A matrices. So this is just an example of how we might call this function. So let's look at propagation here in this question. So if you have a matrix vector set AB that represents n identical operations, the question is, can you uniquely determine each operation, or the matrix and vector for each operation? So this is sort of the inverse of propagating. So the answer options are yes always, no never, sometimes, but multiple solutions for rotations, and none of these. So the correct answer here is C. So the A sub k matrix is simply the nth root of the overall A matrix, and then the B sub k can be solved. A challenge, though, is if A represents, for example, a 180-degree rotation, and you have 3 cycles here, then the individual A matrices that lead to this could represent rotations of plus 60 degrees or minus 60 degrees or other values. So there's an ambiguity with the rotations, but it's interesting to think about whether you can break these down. So now let's look at that example again and do a little bit more compact solution to this. So again, we have this short TR inversion recovery sequence here with the parameters as shown before. So we can look at our operations here, and the operations are the same as before. But now how we do the MATLAB, we can actually do this quite quickly. So we can basically go right to our overall A and B and our steady state here, and we can call MATLAB functions here as arguments to this AB prop. So we're simply going to do relaxation over interval 3 here. We're going to pass it the inversion pulse here. We're going to pass it relaxation over the inversion time interval. We're going to pass it the AB matrix for the excitation, the 90-degree excitation, and relaxation up to the echo time. So that's one single function call to simulate this whole entire sequence, as long as we pass it the correct arguments, which we of course have to be careful about. And of course that gives us MSS, and it gives us exactly the same answer that we saw before. So this is to show you that you can simulate these sequences really in one line of MATLAB code if you want to do it that way. Okay, so let's look at another example. Really the remainder of this lecture is mostly examples now. So let's simulate the pair of an RF and a gradient. So here is your RF and here is your gradient. Okay, now here we've used an RF that has a time bandwidth product of 4, and this relates to the number of lobes in the sync pulse. We have 4 cycles of rotation induced by a gradient over the slice. And notice the 4s correspond here. So the higher the time bandwidth product, the more cycles you will actually induce during the excitation, which actually allows you to make a sharper excitation profile. So we're going to use the complex M vector here for each position along Z here, and this will make it easier to apply the gradient. So the example code here is example 7 from the lecture examples, and this is the core loop. So there's some initialization to set this up. But basically we're going to go through all points within the RF, all samples, and we're basically going to take the rotation matrix for that sample and transform it into the complex M representation here. So we have the rotation on the kth cycle of the RF. We're going to apply the gradient to MC as well as applying the rotation. And then we're going to actually extract the point, the real representation of this, but this just makes plotting easier so that we can actually view this and animate it. So if we do this, this is what this looks like. So the video plays quite quickly, and you notice at the end of the video here we have a beautiful slice profile that's been excited. The magnetization is all in phase. So we can back this up and play this over time, and essentially at each loop we're going to plot the magnetization across a range of Z here. And we're just plotting the transverse magnetization. So we start with very little. You can see the cycles evolving over the pulse here, and you can see that as the magnetization is tipped, the pulse profile grows, and then over the course of the pulse that profile actually gets sharper, but the magnetization is dephased a bit, so it's a little bit hard to see. And as we get near the end of the pulse, we start to rephase with that rephaser gradient, which will actually bring all this magnetization nicely together to be relatively in phase. or refocused. Okay. So that simulation has been done relatively easily, again, using matrix operations. Okay, so now let's look at another example. This one's a bit more verbose if you look at the MATLAB code, so I won't show the MATLAB code here. But what we have here is we have a 90-degree excitation pulse. Again, we've broken it into time samples of 4 microseconds, which is actually typical of real MRI systems. We have 3 sync cycles in this pulse. We have a 2 millisecond duration here. So this is a time bandwidth 6 pulse. So if we look at the 2 millisecond duration, we'll end up with a bandwidth of 3 kilohertz. This is the area of the pulse. So if we look at the area of the pulse, this gives us, if we multiply this by gamma, this will give us the flip angle. And this gives us the flip angle at the center of the profile. Okay, now if we apply this gradient here, we've basically applied 1 kilohertz per centimeter. So this would give us a slice width that is 3 centimeters, sorry. Okay, so in this simulation, what we're going to do is we're going to loop over the positions, and at each position, for each position, we're going to define the rotation at that position. And we're going to loop over time, where we loop through the rotation due to the gradient and the rotation due to the RF. So we're basically doing the hard pulse approximation here, and we're going to plot the magnetization over both time and space. So if we look at this plot on the right here, we have the mx, my, and mz as a function of t. So you notice that we start at equilibrium, and over the course of the pulse, you can actually see the output of the pulse as the magnetization goes towards negative x in this case. As a function of position, we can see that this is the overall profile. We haven't refocused this pulse, so you can see that there's some oscillation in this pulse. And in fact, you can see that there's about 3 cycles here, or sorry, 6 cycles across the whole pulse profile. Okay, and that corresponds to a time bandwidth of 6. Here is the excitation profile here, and this is the remaining longitudinal magnetization in the bottom right. So we can animate what happens here as well. This is as a function of position. So this is similar to the previous example. You can see the profile growing. Now here we're plotting the magnitude, the real part and imaginary part, and the overall magnitude. So you can see how we continue to dephase until the end of the RF pulse. And we get the same profile here that you see in the top right of the plot on the right. Okay, so now we can apply the same example very, very easily once we've written that code, and now we can apply this with 2 kilohertz of off resonance. So the first thing is to think about, well, what should happen if we apply 2 kilohertz of off resonance? The easy thing is to look at the fact that our gradient is giving us 1 kilohertz per centimeter. So if the gradient gives us 1 kilohertz per centimeter, it seems reasonable to believe that 2 kilohertz of off resonance will give us a 2 centimeter shift in this profile. So if we look at this example here, this was our initial plot of the magnetization over time and the profiles as a function of position on the right. If we have off resonance, you'll see that indeed we've shifted this profile by exactly 2 centimeters. Notice that the mx, my, and mz are plotted at position 0. So mx and my actually go back to more or less 0, and the longitudinal magnetization actually goes back to 1. So what you see on the left of this is really a little arbitrary, but what you're seeing is sort of at the edge of the slice what's happening to the magnetization. So the point of this example is really just to show you that once you have this coded up, you can simulate a lot of different effects here. Okay, so now we'll do an example of excitation recovery, but with a real RF pulse. So now the RF pulse is no longer an instantaneous RF pulse here. So we're going to have a 30-degree flip, and we're going to go over TR, and we're going to neglect the transverse magnetization at the end of the TR. And this is in example 9 of the lecture notes, for the MATLAB examples. So we're going to simulate the full pulse and position. We're going to do perfect spoiling, so we keep only mz at the end. We're going to do a matrix propagation here to calculate the steady state at each position. So we're going to propagate through all of the rotations for each position. Okay, so we start with the end of the RF to the TR. So we're basically going to multiply by a spoiling matrix after we've multiplied by a relaxation matrix. And then we can look over the RF. Over the RF here, we're going to have some relaxation that we're actually going to model here, times the rotation due to the gradient, times the rotation due to the RF at each interval. So we're doing a full Bloch simulation here. So first, let's just look at, for the given T1 and T2, which you can see in the MATLAB file here, we have a signal versus flip angle plot here. And recall that for a short sequence like this, because of saturation effects, there's a flip angle called the Ernst angle, where we actually get the highest signal. And that's the plot that's seen here, which is the signal as a function of flip angle. I apologize that the axes are mislabeled here. So now we can plot the flip angle as a function of position for that RF pulse here. And we show the Ernst angle here, and notice that we're trying to get a 30-degree flip angle, so this is actually much higher than the Ernst angle. So we can actually look at the width of this, and then we can actually look at what the result of the simulation is. So this is the signal as a function of position. And you notice that the signal actually doesn't peak in the middle of the slice anymore. And the reason for this is the signal is going to peak where the flip angle is actually equal to the Ernst angle. So it's interesting that we would do better here if we reduce the flip angle so we don't have these big peaks on the edge of the slice. Okay, so this is an example of an adiabatic pulse, and this example is really just put in because adiabatic pulses, if any of you have seen adiabatic pulses, they're not necessarily very intuitive, but basically what's happening is the frequency is actually swept during the B1 pulse, and this creates an effective B1 that actually rotates, in this case, from the positive z-axis to the negative mz axis, and the magnetization will sort of track this pulse here. So if you run this adiabatic function, you can generate this pulse here and simulate it for this example here. And this is an example using a peak B1 here in this pulse, as shown in the plot on the right of 15 microtesla. Okay, and the magnetization here is shown by the white arrow here. The B1 is shown by the yellow, but notice the frequency is actually just given by the rotation about the axis here. So we can do this by doubling the amplitude of the B1 here. And then what you see is that the magnetization actually tracks that pulse a bit better, tracks that effective B1 a bit better. Now the effective B1 is shown by the gray vector here. So we can actually go back and play this last one again here. Okay, so if we start at the top here, you see the effective magnetization shown by the gray, and the white is actually tracking that gray fairly well. And we sometimes say it's spin locked to that gray. Now in this case, we could play a much stronger magnetization and it would really track this much better, but this comes at a cost of increased RF energy. And if we go and play the other video, you see that it doesn't track quite as well at the lower B1, but it still does quite well in terms of applying an inversion, and the inversion here is our goal. So this is just an example of using these matrix simulations of pulses to try to understand better what the pulses actually do. Okay, so this is our final example of this lecture here, and you'll see this example much more in future lectures. Here now what we have is a 30-degree excitation, but it's an instantaneous excitation. We have a TR of 10 milliseconds, and we have an applied gradient that induces exactly one cycle across our voxel. Now here we're not going to neglect the transverse magnetization at the end of the TR. And you can see from the T1 and T2 here that there's definitely going to be residual magnetization at the end of the TR. So we can do this using either a real or a complex matrix representation. We're going to simulate the excitation, and then we're going to simulate the relaxation and gradient effects. So this is the core loop using the complex vector representation. You see here that we propagate the magnetization through relaxation, followed by applying the gradient twist using a simple phase multiplier, and then applying the excitation, so that at the end we will see the effect right after the RF pulse. So in this example we go through the for loop, and then we plot the magnetization at the end, which you see at the right. So you could also look at the MATLAB code, and you can plot the magnetization within the loop to see how it changes over time. So we will see this example again in future lectures, and the main comment we want to make is that you will notice that the magnetization is different from if we neglect the transverse magnetization at the end of the TR. We will go over this concept more. And in this case, in the bottom left of the plots here, you can see that the magnetization is actually tipped 15 degrees away from the z-axis. So let's look at this example with a question. So in this example, the question is there a signal immediately before the RF pulse? So think about this. So the possible answers are no, yes, substantial signal, yes, but very small, and none of these. So to see this example, remember I said that the spins just after the RF are in a plane that's tilted 15 degrees from the MZ axis. So if we simply go backwards through the RF pulse, this plane must have come from being at minus 15 degrees from the MZ axis before the RF pulse, which means that we had almost all of the signal right before the RF pulse. So we will see this much more later as well. So this brings us to the end of the lecture. So to summarize the concepts in these examples, remember that the matrix steady state is easily solved as shown here. Transients often include both rotation and attenuation. The hard pulse approximation for RF and precession includes breaking the pulses up into small time intervals so that these rotations are very small, and in that case the order in which we apply them does not matter. We can extend the hard pulse approximation to a full Bloch simulation, as you saw in the example with a steady state sequence and a real RF pulse. And you can also do brute force simulations over both space and time dimensions, and we'll see how these can be extended. So to understand how we can put this together to even more efficiently simulate multiple spins in more complicated sequences, you can follow the next lecture, which will be lecture number 4.